All right, so in this chapter, we're going to talk about magnetic fields, just magnetic fields. And then in the next chapter, we'll learn that moving charged particles produce magnetic fields. Okay, these are the Maxwell's equations. You've seen them before. I mean, you will study them as in higher level classes. But what these equations do is tell you is on the right-hand side is what? What do you have on the right-hand side? These are the causes. These are the effects on the left-hand side. Okay? Charges produce electric fields. The form of the equation just tells you what the configuration of the two is, how the two are related. So for instance, you already know this. What kind of fields does this charge produce? It produces fields that are radiating away, whose magnitude decreases and so on. And that's what this equation tells you. Okay? That equation will tell you that. This equation tells you moving charges produce magnetic fields. There's something else that the equation tells you. Time-varying electric fields produce magnetic fields. And there is symmetry to that. Well, time-varying magnetic fields produce electric fields. Okay? Now, it turns out that the nature of this electric field is quite different from the nature of that electric field. Okay? But we'll come to that in a couple of chapters. Okay? So right now, we're just going to talk about magnetic fields. And how do you detect this magnetic field? We'll talk about that in this chapter. How do you detect something?
Whatever causes it.
But it needs to have an effect on something to detect it. Okay? And so if you have a moving charged particle, that moving charged particle will experience a force. And that's how you detect it. Okay? All right, so that's where we're headed. Okay? There's a bunch of slides here, so I'm going to go over them quickly. Okay? Now, whenever you talk about magnetic fields, first thing that comes to mind is magnets. All right, so we just said a minute ago, moving charges produce magnetic fields. Where are the moving charges here?
Along the magnetic field lines.
No. Moving charges are producing the magnetic field.
Oh, sorry.
Yeah, so where are the moving charges in this thing? So every atom has a bunch of electrons, and what are the electrons doing? The electrons are moving. Okay. Now I'm giving you loose. We're talking loosely, but anyway, let's. This is very loose talk. Okay. All right, so here's a lithium atom. This actually is in 2s orbital. Okay, so in an s orbital, the electron goes around like that. What you need is an electron going around in circles to produce a magnetic field, and you learn details. Okay. So actually, let's do boron. So we'll do boron. Okay, there you go. So this is the 2p orbital. Boron has 5 electrons, and this electron will produce a magnetic field. Okay, so this you'll learn in the next chapter, and we'll tell you about it right now. So you have a circular current like this. It'll produce a magnetic field just like a bar magnet. Okay. So what you do is you stick your fingers in the direction of the current, your thumb points in the direction of the magnet. Okay. So this current produces a magnetic field like that. Yeah. Does this magnetic field look familiar?
Looks like Earth's magnetic field.
Very good. So go from A to B. What do you conclude from that?
Earth is spinning.
That is true. No, there must be a current inside the Earth. Where is the current?
In the outer core.
Outer core, liquid outer core. Okay? And what does that also tell you? It must be a conducting liquid outer core. All right? So, let's extend that argument. Anytime a planet has a magnetic field, it must have a metallic liquid core. Okay? Where there's a current flowing. Okay. All right. Anyway, so we went far. So what you need is, so the currents are in the atoms themselves. Okay? And I mean, there's more to that picture. But so is every atom a magnet? All right, well, if you have two electrons in this orbital, it turns out that if this guy is moving in this direction, this guy will be moving in that direction, the magnetic field cancels out. So you have to have an odd number of electrons in general, okay, for it to exhibit magnetic behavior. All right, so anyway, so now let's get back to this, these magnets. Now you'll see if you study these magnets, every magnet has two poles. Okay. The reason we mentioned this is it's different than electric charges. You can go by a positive charge by itself, you can go by a negative charge by itself. Okay, but you go by a magnet, they'll sell you both the poles together. Okay. And of course, just like charges, like poles repel each other. Okay, like poles repel each other, and unlike poles attract each other. So these guys will attract each other. Okay. You break a magnet, what happens? You get two magnets. Again, loosely speaking, break that, what do you get? Four magnets now. Yep. How far can you go?
To two atoms.
Yep. No, to a single atom. Yep. So that current, so again, behaves. Okay, it's the magnetic field is like that. All right. Unlike electric charges, magnetic poles have always been observed in pairs. Okay. However, magnetic monopoles, when you hear that term, monopole just means a pole by itself, are postulated by some theories. We've never seen them. Okay. All right. Now I said that, how do you detect a magnetic field? Moving charges. Yeah. So other magnets have moving charges in them. Okay, so right now we're not, so you can detect a magnet with other little magnets. So here's a big magnet, it's created magnetic field around it. How far does this field extend? Infinite. Okay, it just gets weaker, just like the electric field, and it gets weaker with the square of the distance. Okay, but if you want to detect a magnetic field around this, you just go by a little magnet, which is a compass, and it will line up along the magnetic field lines. Okay, so the convention is there are the field lines. Field lines start at the North Pole and end at the South Pole. Magnetic field lines are denoted by B. They are a vector field. What does that mean? Okay. For now, we're not considering time dependence, okay? But at every point you associate a vector. So there's a magnetic field there, like that, and so on, okay? So they're a vector field. Field lines around a bar magnet can be traced using a small compass. Okay, that's what. Magnetic fields at a point can be defined in terms of the force they exert on a moving charged particle. Okay, so what does this mean? If you ask the question, what is the magnetic field at this point? You can measure the magnetic field at that point by figuring out the force on a moving charged particle at that point. Okay? So it's a vector field. Okay, it has magnitude and direction. Okay, so here's the equation, important equation that you need to understand. So F for force, the subscript B telling you that it's the force due to a magnetic field, and the magnetic field is on a moving charged particle. That's the charge, that's the velocity of the particle. Okay, so the force is V cross B. Okay. And of course, I'll state the obvious. If the field B is zero, the force is zero, of course. If there's no field, there won't be any force. If the charge is zero, the force is zero. So on a neutral particle, you don't have a force. If you have a charged particle and it's not moving, then the force is zero. Okay? So it tells you all of that. All right, so let's say you might know this. So if you want to speed up an object, if an object is moving in this direction, and if you want to speed it up, what you have to do is you have to apply a force in that direction, in the direction in which it moves. If an object is moving and you apply that's a trajectory, and you apply a force in this direction, what happens?
Starts moving at an angle.
It gets deflected, but it won't speed up. Okay, so when you apply a force perpendicular to its motion, you can't speed it up. You can change the direction of its velocity. All right, so we want to understand this force. Okay, so if here's a charged particle, let's say the magnetic field is in this direction, and there is the velocity, the charge is moving in this direction, V cross B is this vector. The force is perpendicular to the plane containing V and B. Okay? And you guys remember the right-hand rule? You take the first vector, V, here's the second vector, V cross B. If you turn a screw this way, which way will the screw move? That way. Okay? So that's the direction of the force. All right, so the force is perpendicular to the velocity vector. So what does that tell you? All that the magnetic force can do is deflect the particle. It can't speed it up. Okay? All right, so the force is always perpendicular to the plane containing that, and you use the right-hand rule to figure out the force. So V, P, and there's the direction of the force. Now, there will be situations when you won't be able to turn your hands in the appropriate direction. So the right-hand screw rule is the best one to remember. V cross B. V cross B, if you turn V to B, the direction in which the screw moves is the direction of the force. Okay? All right, so here's the magnitude of the force. The magnitude of the force is, for the cross product, you know that the magnitude, again, let me remind you, A cross B, so for two vectors, A, B, theta, the magnitude of AB is magnitude of A and magnitude of B times sine theta. What is sine of 0?
0.
0. What is sine of 180?
Negative 0.
So 0. Okay. So what this is saying is, what this is saying is, the cross product of parallel and anti-parallel vectors are 0. Okay. So if the particle is moving either parallel to the magnetic field or anti-parallel to the magnetic field, the force on it will be 0. Okay. All right, so become friendly with this equation. All right, so again, this right-hand rule tells you the direction of the force, and the magnetic force can only deflect the particle, it won't speed it up. Okay. You want to speed up a particle, what do you have to do? You have to use an electric field. Why is that? Because the electric field will apply, if you apply an electric field in this direction, the force will be in that direction. Okay? The force is always in the direction of the electric field, so just point the electric field any way you want, and you can point the electric field in the appropriate direction, and you can speed up the particle. Okay. You guys understand so far? Okay. So again, there's the velocity, magnetic field, and there's the force. Okay. Electric forces on charged particles is in the same direction as the field, whereas the magnetic force is perpendicular to the direction. Okay. Since magnetic force is perpendicular to the direction of motion of the charged particle, it can do no work on the particle and hence cannot change its energy. Okay. So when you apply force perpendicular to its motion, you cannot do any work on the object. And you have to do work on the object to either increase or decrease its energy. Yeah. Okay, we'll talk about the units in which the magnetic fields are measured. So whenever you want to look at units, you just go find an equation that involves that quantity. Okay, so here's the magnetic field, and we want to find the units of the magnetic field. So the magnetic field, now we'll just write F as far as units is concerned, this will be true. Okay, so magnetic field is force divided by Q over B. What are the units for force? Newtons. What are the units for charge? Coulombs. Velocity is meters per second. Okay, so we don't like to write a mess of units. So what do? We just give it a new name, a new unit. And this combination is called a Tesla, after Mr. Nikola Tesla. Yeah. Notice, by the way, charge per second is an ampere. So this is also equal to Newton ampere meter. Okay. And this combination is called a Tesla. Okay. Now, a Tesla is a very strong field. We don't encounter it normally. For instance, in this room, the field is about 1/10,000th of a Tesla. Okay. So you can go on any planet, and the planetary fields are about 10,000th of a Tesla. You want a Tesla field, you can go to the surface of the sun and you can get that kind of stuff. But if you don't like the heat, so we define a new unit called the Gauss, which is appropriate for planetary fields, and 10,000 Gauss is 1 Tesla. Or 1 Gauss is 1/10,000th of a Tesla. Okay. But the SI unit for magnetic field is a Tesla. Okay. Yeah, so here are some fields in Teslas. A strong lab magnet is 30 Tesla. And you guys can MRI machines are 1 to 3 Teslas. Okay, so on the surface of the sun, it's 100th of a Tesla. Okay. On the surface of a planet, it's on the surface of the Earth, it's 10,000th of a Tesla. Inside your brain, the magnetic field is 10 to the power of minus 13 Tesla. Why is there a magnetic field inside your brain?
Electrical signals.
Right, every time a charge moves, it produces a magnetic field. So every time a neuron fires, there's charges moving. And so in fact, let's say you're thinking about if you're using this part of the brain, there's currents there and this magnetic field is strongest there, and you can detect that magnetic field without having to, So you can put little coils there. See, there you go. There. So those are all coils detecting the magnetic field. No, those are, wait a second. Okay, that's detecting voltages. So what is the term for? Okay, the term escapes me right now, but it's similarly done. Okay, brain post. So there, so here the neurons are firing, and this is detecting the.
I think it's called an MEG, magnetoencephalography.
Encephalography.
Yeah,
Okay.
MEG.
Yeah. Okay, so there you go. That's so. But they have helmets, and with very similar. They're called squids, little coils to detect the magnetic field. Yeah. And so you can detect magnetic fields. Squids are sensitive enough to detect up to magnetic fields up to 10,000 stun, weaker than this. So, yeah, so you can detect what part of the brain is active for various tasks and stuff like that. Okay, so here's Earth's magnetic fields. So planetary magnetic fields are of the order of a Gauss. The Earth's magnetic field is half a Gauss. Okay, so this shows you, of course, it's not constant everywhere, and this shows you the magnitude. Okay, so near the poles it's stronger and so on. And of course, the Earth's magnetic field, Okay, so there's the North Pole, and there's the South Pole of the Earth. The Earth's magnetic field is produced by a current, like that. So the North Pole of the magnet is under the South Pole. Okay. All right, so here's the neat thing about this magnet. This current is steady for a long time, on the average a quarter of a million years. Okay, and then in a blink of an eye, 2 to 5,000 years, it will switch directions. We don't know why. So if it switched directions, now the magnetic field points this way. So all your compasses would be pointing in the opposite direction. We're in the middle of a switch, apparently. How do we know the switch happens?
You can watch the drift in the magnetic field.
You can't watch for 2,000 years.
Pretty sensitive equipment.
There's evidence in rocks for the
Very good. So,
patterns.
mhm. Okay, so there's stuff coming. This is the Mid-Atlantic Ridge. You guys know the Mid-Atlantic Ridge? Do I need to pull up a map of that? All right, so there's magma coming, oozing up there, and that has magnetic material. Okay, so this is new rock being laid. So this is current rock. This was laid 800,000 years ago. That one was laid 1,000,000 years ago, and so on. Okay, so the magnetic field, the magnets on this rock are pointing in this direction. The magnets in this rock are pointing in that direction, and they record the Earth's magnetic field. Yeah. So that's how we know. So after World War II, when we were mapping the sea floor, ocean floor, that's when we learned about this. So this is fairly new knowledge. All right. Now, when we deal with forces that magnetic fields apply, we'll be dealing with three-dimensional stuff. So here's how we indicate magnetic fields. If it's coming out of the sheet, then what you want to do is think of an arrow. And so if you're looking at the arrowhead, you're looking at these points. So if the magnetic field is coming out of the sheet, you're looking at the arrowhead, and this is how we indicate that. And if the magnetic field is going into the plane, you're looking at the tail of the arrow, and we indicate that by crosses. And of course, if the magnetic field is in the plane, you can always draw it like that. Okay. All right. So, how do we detect a magnetic field? A moving charge, because the magnetic field exerts a force on a moving charge. What is a current? What is an electric current? It's a bunch of moving charges. So if you have a wire carrying a current in the presence of a magnetic field, the magnetic field will exert a force on every charge, and as a result, there will be a force on that wire. Okay? Because the force on every charge is in the same direction, and the wire will be deflected that way. Okay, so here's the force on a single charge in a current carrying conductor. See, that's the density of charges, and that's the volume of the wire in the magnetic field. So that gives you the total number of charges. So this is the force on a single charge times the total number of charges gives you the net force on this wire. Okay? And if you guys look up your notes, current is given by Q times the drift velocity times N times area. Okay? And so these guys are combined into the current. L is that. Okay? So let's figure out the direction of this force. In this wire, the charges are moving in this direction. What is the direction of the magnetic field? Into the paper. Okay? And V cross B, if you turn a screw from here to there, it'll be deflected that way. That's the direction of the force. Okay? So, okay, V cross B be deflected in this direction. Okay? So what we do is to write this formula in a compact form, we'll call the L vector. What is the L vector? The L vector is the length of the wire length of the wire that is in the magnetic field. Okay, so the length is defined by what is in the magnetic field. You don't count the wire outside the magnetic field. And what is the direction of the L vector?
The direction that charge is flowing.
The direction of the current, the direction in which the charge is flowing. So if the current is flowing in this direction, now the L vector would point that. Okay? So the force on a current carrying conductor can be written in this compact form. I L cross B. Okay? And again, so what would be the force if there's no current? If the current is zero, the force will be zero. If the magnetic field is zero, the force will be zero. If the current is outside the magnetic field, L will be zero, and there's no current, no force. Okay? So you have to have a current carrying conductor inside a magnetic field to feel the force. Okay? So yeah. And that's the force. Okay, so we gave this formula to you for a straight wire. Again. Now, since you guys are calculus experts, we'll do it for a bent wire. Well, what does calculus teach you? If you have a bent wire and if you know the formula for a straight wire, what is the natural thing to do? Chop it up into little straight pieces. Okay? So there's this bent wire. We'll chop it up into this straight piece. I know the force on this little straight piece. And then I want to add it over all the little pieces. What is addition called in calculus? Integration. Yep. And so we're going to add it all up. Now in general, if B was varying with distance and all, this would be hard integral to do, but here's the expression in general. Okay, now let's consider the case where B is constant. That is, B is uniform. What does that mean? Its magnitude and direction are the same everywhere. Okay? If this is constant, that comes out of the integral. And then it's just a matter of, and of course the current is the same everywhere in the wire. And then it's just a matter of adding up all these vectors. See, adding up all those vectors is, the sum of all those vectors is the vector from the starting point to the end point. So the force on this wire is the same as the force on this wire and the force on a billion other wires. So as long as you have the same endpoint, the force on you is the same in a uniform magnetic field. That's not true if the field is not uniform, but in a uniform magnetic field, in a uniform field, force on all wires carrying the same current with the same endpoints are equal. What is the sum of all these little vectors?
0.
0. The force on a loop is 0. The net force on a closed loop is 0. But there's a very interesting thing. All right, so before I talk about that, let me set you guys up. What is the force on this guy? 0. So there's the center of mass of this guy. Will anything happen to this guy?
Nope.
No. What's the force on this guy? 0. Will anything happen to this guy? It'll rotate. So net force of 0 doesn't necessarily mean net torque is 0. Okay? And that turns out to be true here as well. Okay? So the net force is 0 in this case, but the net torque is not 0. Okay, so let's look at that. All right, so we're going to put a current carrying loop in a uniform magnetic field. Okay, so let's figure out the forces on this thing. And since I'm recording this, I gotta put it on here as well. So here is L, here is B. L cross B, yeah, L, B. If you turn from L to B, the force, L to B, the force is coming out of the paper. Okay? L to B, force is coming out of the paper. On this guy, the force is in that direction. The lengths are equal, the currents are equal, so these forces are equal. What about the forces on this guy?
0.
Yeah, so this is parallel and this is anti-parallel. The forces on these is 0. The net force is 0 on this loop, but these two forces will turn the loop. So if this is the axis, they'll turn it like that. Did you guys understand this? You have a magnetic field. What you did was you took a loop of wire and passed a current on this loop of wire, and the magnetic field exerted a torque on it. It made it spin. That's an electric motor. That's what does 90% of the world's work. That diagram right there. What did you end up doing?
Converted electrical energy to work.
That's right, to mechanical energy. Okay, so that's how you did it. So again, here's a magnetic field. You passed a current like that, and this thing turned. All right, so we want an easy way for this to remember this. Okay, so let's figure out an easy way to remember this. Okay. So what we'll do is we'll define, just like we had defined a length vector, we'll define an area vector. Okay. The area vector for this loop, okay, the area vector for this loop is going to be, the magnitude of the area vector is just the magnitude of the area. And the direction of the area vector is like this. You'll always use your right hand, point your fingers in the direction of the current, and your thumb points in the direction of the area vector. So this will be the area vector. Okay? Your fingers point in the direction of the current and the thumb points in. Okay? So what is the magnetic field trying to do? It's trying to line up the area vector with the magnetic field. That's how it turns. Okay? All right. So How do you make a motor? You have you set a north pole here, a south pole here. You get a magnetic field like that. You put a coil of wire in between there. Here's the area vector, and the area vector lines up with the magnetic field. Now what do you do?
Put another one in between that keeps spinning.
Now you can switch the direction of the current.
That's reverse. Flipping the polarity.
I'm sorry?
Flipping the polarity.
Yeah. So you do it. So okay. So here's a way to do that. Okay. So if the connections are through brushes like that, you're switching the current direction in just the right time. You know. So this is the basic picture of an electric motor. Okay. So you can see that point to. There's the current, there's the area vector, it's lining up like that. And then once it lines up, then you flip the current, it'll be pointing like that. So you keep rotating it. Okay. So this is, electric motors are a very important part of your life, and now you know how they work. Okay, I want to finish the lecture on this before okay. So, on a current loop, the net force on a closed loop is 0. Net force on the current loop in a uniform magnetic field is 0. In a non-uniform field, the force will be non-zero because the force on this side will be different than this side and so on. Okay. However, the torque is not 0. Okay, so in a uniform field, the torque is not 0. So this thing is, here's a top view. Anyway, we won't try and confuse with this. So the force on this guy is in this direction, the force on that guy is in that direction, and this guy will rotate like that. Okay, so the area vector will line up with the magnetic field. Yep. When will these forces go to 0? Can you?
Area vector is pointing in the direction of the magnetic field.
Yeah, or if you stop passing the current, there won't be any forces and there won't be any torque. And the electric motor doesn't work when there's no current in. The maximum torque is I, the current flowing, times the area, times B. Okay, so, and if you want to increase the torque, what you can do is have more loops. Then the formula becomes N times I times A times B. N is the number of loops of wire. Okay. So the torque is I times A times B times sine theta, where A, there's B, and theta is the angle between A and B. Okay. So the torque is 0 when area vector is parallel to the magnetic field, so sine theta is 0. Okay. And it's 0 when it's 180 degrees as well. Okay. So the torque is that. So the torque on the current carrying loop rotates vector A towards the magnetic field B. Okay. So the torque will line up with the magnetic field B. Okay, we define something called the magnetic moment. Okay. The magnetic moment tells you how strong a magnet it is. Okay. So here is a current carrying loop. You saw that it behaves like a magnet because the magnetic field around the loop are, okay, so you have the current carrying loop and it produces a magnetic field around it just like that of a bar magnet. So this current carrying loop is called an electromagnet. This guy is called an electromagnet. And the strength of that magnet is N is the number of loops of wire, I is the current flowing in the loop, and A is the area of the loop. What would you rather have, an electromagnet or a real magnet? Or a magnet, or a permanent magnet?
Electromagnet,
Why?
you control the magnetic field and current.
You can turn it on and off. You can switch directions. Yep. So you have a lot of versatility. What's the price you're paying?
You have to spend energy on it.
Right. Every time you use it, you just gotta spend money on it. Yep. But they're very versatile. So electromagnets are very useful. Okay, so the torque is this magnetic moment crossed with B. Okay, so so a Tesla provides a lot of torque, good acceleration. Okay? So it has a strong magnetic moment on that wire. Lots of loops and stuff like that. Okay, we won't worry about this. Okay, so there is an electromagnet that if your fingers point in the direction of the flow of current, your thumb points in the direction of the magnetic moment. Okay. Of course, so what does this guy have? Gravitational potential energy. You let go, you can convert that to kinetic energy. Just like that, if you have this magnet and you put it in a magnetic field like this magnet will want it, the magnetic field will make it want to turn this way. So it's converting potential energy to kinetic energy. Yeah. So there's the potential energy of the magnet moment in the magnetic field. Okay? It's mu dot B. So its potential energy is minimum when it's lined up with the magnetic field, and it's maximum when it's pointing in the opposite direction. Okay, this kind of stuff are useful. So you can turn satellites up there. So what you do is, so here's a satellite up there, 500 miles up. You're using this to bounce TV signals off. And let's say now you want to broadcast to those people, and you want to turn the satellite that way. You're not going to send somebody up there to, okay? So what you can do is, you can use a coil, pass a current in this coil, and the coil will turn toward the magnetic field. The satellite will turn the other way. Okay? Yeah. So the total angular momentum of this guy is 0, and it'll remain 0. Okay. So you can use that to turn satellites. Okay. Many satellites use coils called torquers to adjust their orientation. Torquers interact with the Earth's magnetic field. Okay. Now, what's the problem with this thing?
With the field switches.
No. Oh, that field switches every 250,000 years. So you can use this for low Earth orbit satellites. For higher Earth orbit satellites, the magnetic field gets weaker. Yeah, so that's the problem. So the advantage of such devices is that they use solar energy rather than thruster fuel. If you could turn satellites using thruster fuel, but then how much do you plan for? You might want to turn the satellite 10 years from now. Okay. And it costs money to put weight up in orbit. So typical values are of the order of magnetic moments are that. Okay, so you see the magnetic field at this elevation at lower orbits is 10 times weaker than on the surface. Okay.
Okay, I found this on the web for the magnetic field elevation. elevation bigger than the surface. Check it out.
Hey, Siri's gotten better. Siri wouldn't understand my accent 4 years ago, or 5 years ago. Okay, so let's see what happens if you throw a charged particle in the presence of a magnetic field. Yeah. So this magnetic field is into the plane. You throw a charge in this direction, so we'll say it's a positive charge. V cross B. V cross B. So you turn a screw from here to there, it'll move in this direction. That's the force. So the particle will be deflected here. When it's moving in this direction, V cross B, the force is there. And so you can figure out that so here is a magnetic field. Here's a beautiful thing that happened. Okay. I threw a particle perpendicular to the magnetic field. And what happened? The particle is making circles around the field now. It got trapped. Well, can you think of why this might be useful?
If you want to speed up a particle.
Well, remember, magnetic forces can't speed up particles.
You want to capture charged particles from the air?
Let's say you want to make a fusion reactor. You heat this gas to millions of degrees. If that gas hit the wall, it would vaporize the wall in a heartbeat. Just make sure that it doesn't hit the wall. So here is this plasma that got trapped around the magnetic field lines and it never hits the walls. Yeah. Now, of course, you learn that the faster you move, the bigger the circle you're going in. So, and the stronger the field, the smaller the circle. Okay? All right, anyway, magnetic field lines can trap charged particles. Okay, so this formula gives you the angular frequency, or the cyclotron frequency as it's called, is 2 pi times the linear frequency. Frequency is the number of circles it makes, revolutions it makes per second. Okay, so the cyclotron frequency is given by the charge, the strength of the magnetic field, and inversely proportional to the mass of the particle. Do you guys need a break, or I want to try and finish this lecture? You good? All right. All right, so this was if you throw it perpendicular to the magnetic field. Okay. All right, so here's the magnetic field. You throw it perpendicular, it just goes in a circle and it's right there. What if you throw it at an angle? All right, well, if you throw it at an angle, this has a perpendicular velocity and a parallel velocity. Remember, the parallel velocity doesn't get affected. The perpendicular velocity makes it go in a circle. So if you have it at an angle, what it ends up doing is a spiral. It spirals along the magnetic field line. Okay? So if you throw it at an angle, it spirals along like that. Okay, so if you don't do anything about it, this particle will leak out. And it will hit that wall. Well, you don't want that wall vaporizing. So how do you solve that problem?
Bend the magnetic field, I assume.
Very good. Make the field inside a donut. Okay? This is all not crazy stuff. There. So this is a fusion reactor, okay? And you have magnetic fields inside donut-shaped things, and that's where the plasma resides. Okay? There you go. There's the plasma. Never hitting the wall. And that thing is millions of degrees Kelvin. Yeah. Princeton University has one, and they have an open house sometime in April. That it's a national facility. Yeah. All right. So here's another way of doing it. This is called a magnetic bottle. Okay. So if you make the field stronger at these ends, see the force is in this direction, and this component of the force will make it go in a circle, and this component of the force will make it reflect. And so the particle will get trapped in that direction as well. And so this is a magnetic bottle. This is not as commonly used. Donut-shaped fields are more commonly used. We have this in nature, okay, but this is stronger fields will reflect the particles back in towards the weaker fields. Okay, so the Earth has magnetic fields, okay, and the sun is, these charged particles from the sun, protons and neutrons escape from the sun. This is called the solar wind, and the Earth has a magnetic field around it. So the field lines are like that, and so these particles coming here get trapped. And the field here is getting stronger, so the particles will go there and get reflected back. They'll go back and forth. They're going fast enough where they'll cover this distance in spiral around the field lines from pole to pole, covering the distance in just a few seconds. So they'll go back and forth in just a few seconds. Now, if these particles happen to come within about 50 miles, they start hitting enough atmospheric molecules, exciting them, and that's the northern lights. Yeah, it's the southern lights as well. Yeah. So the solar wind are the charged particles, and they get trapped. Okay. So they're named after Mr. Van Allen, who discovered them, and they extend from 1,000 kilometers to 45,000 kilometers. The radius of the Earth is 6,400 kilometers, so about 7 times the radius of the Earth. Okay. So you have these. So there's the Earth, and there are these donut-shaped charged particles, shells of charged particles, where the particles are going back and forth.
Or are they just trapped there forever? Like once they get into the field, after coming from the solar winds, or?
Well, they're losing energy because when they're going in circles, they're accelerating and they're radiating energy and stuff like that. So eventually they leak up. But you have a constant supply. So I imagine their density is constant. But that's a chat GPT question. I don't know the answer. What's your favorite? What is AI tool? What do you guys? Gemini. All right.
They don't have a limit.
Hmm?
They don't have a limit on one of theirs. Seems fun to ask it stuff.
Chat GPT has limits?
ChatGPT, you can only upload like a certain amount of photos. Gemini
Mm.
just lets you keep going.
Mm.
It's pretty good.
There's no
Mm.
limit for text, though. I don't think.
Yeah.
Mm-hmm. Yeah.
And sometimes it has like a set way it wants to do something. It doesn't want to do it any other way.
I see.
It's like if you ask this, I asked it to solve something with kinetic energy,
Mhm.
and it continuously wanted to use force times distance instead of 1/2 mv squared.
Mm-hmm.
I couldn't get it to do the other way.
I see. I see. All right, so here are these donut-shaped shells around the Earth, okay? So the solar wind has particles, protons and electrons. All right, so when these particles come close enough, within 50 miles, these particles will bump into the atmospheric molecules, excite them, and you guys know how an atom emits light, right? So this is what was this?
One.
I got to remove one of these guys. Now it's a boron. Okay, so you hit this guy with a hammer. This electron gets excited there, and then when he falls back, he'll emit a photon. Okay. So or if you have ionized it, and when an electron falls back, also he'll emit a photon. Anyway, okay, a de-exciting atom will emit a photon. Okay, so these particles bump into the atmospheric molecules, they excite them, and when the molecules de-excite, they emit photons. Okay, the various colors being, okay, so oxygen emissions are green, so that's the oxygen molecule excited. Brownish red or brownish red. Nitrogen emissions are blue or green. Okay, so that's nitrogen. That's nitrogen and so on. Okay. Red if returning to the ground state from an excited state. So this was returning to the ground state. Okay. And of course there are various levels. In the southern hemisphere, they're called aurora australis. So we look for these things. So Jupiter, here are Jupiter's auroras. So why do we look for this thing? Now we know that Jupiter has a magnetic field and so on. Okay. Many other implications. There are Saturn's auroras. Velocity selector. Okay. So here's an important device in research. Okay, what you'll need is, oftentimes in research, you need a charged particle beam, and not only that, when you produce a charged particle beam, oftentimes those particles are all going at different velocities. So, for instance, you can just heat a wire, and it'll spit out electrons. Okay, and if it is at a negative potential, it will spit out electrons. But these electrons are not all at the same, coming out at the same speed. So you want to be able to choose electrons going at the same speed. Okay. Here's a velocity selector. Okay, so here's a source of the charged particles. And if you have a magnetic field crossed, so you see the magnetic field and electric field are perpendicular to each other. If this is a positive charge, the electric force on it is in this direction, and V cross B, the force is in that direction. This force depends on the velocity. So only particles with the right velocity where this force equals this force will go straight through. If they're moving too fast, they'll deflect and hit that. If they're moving too slow, they'll be deflected and hit this plate. Okay. So this device gives you particles of precisely that velocity. So here's the velocity selector. All right, well, what can we do? I guess so with this thing. So you learned that earlier. You learned that if you have a charged particle and you throw it in the presence of a magnetic field, it goes in a circular orbit. Okay. And well, the frequency and okay, so this is V over R. The radius is related to the mass, the radius of the orbit. Greater the mass of the orbit, greater the radius of the orbit. All right, now we're going to use this idea. Okay, every time you learn something new, it needs to get bulbs firing in your brain. Okay, so we use this device. We had a charged particle and we got a particle with a particular velocity. And now we're going to send it in another magnetic field, and this charged particle will go in a circular orbit. And the radius of this orbit is related to the mass of this particle. The more massive a particle, the bigger the radius. And that's how every atom is weighed. So you want to weigh an atom, what do? You ionize it, you shoot it at a particular speed, pass it through this magnetic field, and measure the radius. And the radius is proxy for the mass. And you can calculate the mass exactly. That's a mass spectrometer. Yeah. So that's how they know all those masses. That's how those were measured, the red numbers. So the one for the hydrogen atom, one atomic unit, mass unit, is 1.67 into 10 to the minus 27 kgs. Okay? And so, of course, neon has 20.1798, so you just multiply that by 20. Okay? We won't talk about the cyclotron. We'll quickly talk about the Hall effect, because you might run into this. So here's a flat wire, so to speak, okay? And you're passing a current through this flat wire. And if you place a magnetic field in there, of course, a current is driven by a voltage and electric field. What happens is, see, the magnetic field deflects these moving charged particles. So let's say the charged particles carrying, so the particles carrying the current are electrons. The electrons at a drift velocity in this direction when the current is like that. So in an ordinary wire, in a copper wire, the electrons are moving this way. V cross B would be a force in this direction, and the magnetic force would be in this direction on a positive charge, but these are electrons, so the force is in that direction. These electrons will be deflected there, and a bunch of electrons will collect on this face of the wire, and this face will become positively charged. So what happens is, if you have here's what's going on. So here's a flat wire. You're passing a current in this direction. The electrons are moving in this direction in the presence of a magnetic field. If electrons are carrying the current, this end will become negative and this end will become positive. You can measure a voltage across this, and that's called the Hall voltage. If positive charges are carrying the current, if negative charges are carrying the current, this end becomes positive, and that if positive charges are carrying, that end becomes negative, and that end becomes positive. So you measure the voltage in a direction perpendicular to the direction of flow, and you can figure out what are the charge carriers. Okay? So the Hall voltage can be used, this voltage is called the Hall voltage. It can be used to measure the magnetic field. It can be used to measure the charge type. It can be used to measure the carrier density. Okay? So the Hall voltage is equal to that. So there is a carrier density, and that's important. I told you that copper has a carrier density, a free electron density of about 10 to the power of 28 per meter cube. Nobody counted it. They used this Hall effect. Yep. I can tell you about MRI machines, how they work, if you want. So you saw how electric motors work. Very important, you need to know that. Do you know how speakers work? Okay, so electromagnets are a big part of your life. Okay, so here, let's figure out how speakers work. So all speakers have a permanent magnet. Okay. What does a speaker do?
It vibrates to create frequencies that you can hear.
So it converts an electrical signal into sound waves, into oscillations. Okay, so you just learned the magic of an electromagnet. Okay, let me pass a current like this. Okay, this current produces a magnet like that. It behaves like a magnet like this. And if the current is in this direction, this coil is attracted this way. We put this coil in a diaphragm. So when the current is like this is attracted this way. When the current is in the opposite direction, it's repelled that way. Okay. So I have this diaphragm. I have a wire. Here's the permanent magnet sitting. Every time I pass a current like this, it gets attracted like this. The current is like that. So I can turn this electrical signal into vibration signal. And that's producing the sound. Okay. All right, so these guys are amazing devices. Okay. You can use them a whole bunch of places. Did you want to hear about MRIs, or we want to take a break? All right,
Finish
but
up the lecture.
huh?
Finish up the lecture.
Oh.
How much longer do we have left? Is it just MRIs or?
Yeah, that's just MRIs, and I'm just going to give you a 30-second view of MRIs. Okay.
Sure, might as well.
What's that?
Might as well. Learn about it.
Okay. So nowadays these are superconducting. So this is it's like a superconducting wire, and it produces a strong uniform magnetic field inside there like that. This is a strong magnetic field, and the strength of this magnetic field is about, let's say, 3 Tesla. That's 10,000 times stronger than the field in this room. Okay. All right, so MRIs use, okay, if you have an electron, every electron is spinning. Okay, what does this guy act like? What is this? A loop of wire carrying a current. This is acting like a magnet, like that, right? An electron spinning, it's moving charges, it also acts like a magnet. A spinning electron is a magnet, okay? If the electron is spinning this way, since it's a negative charge, it's a magnet pointing in this direction. A proton is also spinning. Where do you find protons?
In the center.
I'm sorry? Go ahead.
In the center of an atom.
Yeah, so the nucleus of a hydrogen atom is a proton. Your body is full of them. You're really mostly a bag of water, and every water molecule has 2 protons. So protons there are plenty. Okay, so here's a spinning proton, and it acts like a magnet. What does the magnetic field want to do? If I put a magnet in a magnetic field, what
So orientate.
it wants to orient it this way. Okay. All right, so we have a strong magnetic field, and we have these protons. Okay, so the magnetic field wants to orient it this way. If a proton is in this direction, this is a higher energy level. This is a low energy level. Okay. Now, quantum mechanically, this proton can only point in 2 ways. Either simplifying this, either this way or that way. Okay. Now we'll draw the energy levels. This is the high energy level, this is the low energy level. This is, the proton is parallel to the magnetic field, this is, proton is anti-parallel to the magnetic field. Okay? All right, the energy difference is proportional to the magnetic field, some constant times the magnetic field. Okay? And so when they put you in this magnetic field, okay, the protons inside your body, they're either lined up with the magnetic field or in the opposite direction, okay? And so their energy level is proportional to the magnetic field. So let me draw this. So here's the magnetic field. This is the proton. You have to be patient with this thing. Okay? How do you excite something? How do you excite an atom?
Give it energy?
I'm sorry?
Give it energy?
Yeah, so you have to give it the right energy. Exactly this energy for the atom to go from here to there. You can do the same thing with the proton, this thing, with the spin. You give it the right energy photon, you can kick this proton from this energy level to that energy level. And it doesn't like to stay there too long. So it absorbs a photon, it went up there, and then when it comes back, it'll emit the photon. And you take a picture of that. Did you guys understand that? I'm just giving you a piecemeal information. We'll put it all together. All right, so we feed you in there. See, this just illustrates how strong the magnetic field is. You flip on the thing, any metal will fly across. People have died on this thing. There have been oxygen cylinders inside the room, and somebody turned this thing on. That's a flying projectile. All right, so this is a high energy level. This is the low energy level. Okay? Now the question is the following. Okay, so your MRI machine can take a picture of a spot about 0.5 millimeter by 0.5 millimeter by 0.5 millimeter. Okay. So how do I take a picture of that spot? Okay, what I do is, so I make the magnetic field different at every location on a grid. Remember, the energy difference depended on the magnetic field strength. Okay, so now if I want to take a picture of that spot, I make the field exactly some value at that point. At every other point, the field is different. I shoot a photon, only that point can absorb that photon. And then wait for it to re-emit the photon, take a picture. Once you're done taking a picture, change that value of the field there, take a picture of that, and so on. And then the computer puts together the image of all the spots. Okay. Gradient magnets are turned on and off very rapidly in a specific manner, altering the main magnetic field at a very local level. This allows one to pick exactly which point to take a picture of. Okay. So that's how MRI machines apply specific energy, RF pulses using coils targeted at the spot being imaged. Pulses cause protons in that area to absorb energy, and they flip from here to there when they absorb energy, and then when they emit the energy back, they go back. This is the resonance part of the MRI, magnetic resonance imaging. When the RF pulse is turned off, protons begin to return to their natural alignment. They fall back, emitting that photon. By emitting the RF photon, the coils now pick up these photons and the information is transformed into an image. Okay. MRI contrasts work by altering local magnetic field in the tissue being examined. Normal and abnormal tissue respond differently to contrast, allowing the visualization of tissue abnormalities and diseases. All right, guys.